Okay, speaking of 8, it's Jamie. You know the score? 3 minutes, let it go. 3, 2, 1, go.
Okay. In 1915, Einstein founded general relativity, which is a theory of how light and matter behave in a strong gravitational field. Now, for 100 years, it's passed every experimental test with flying colours, from tiny deviations in the orbits of planets to how light bends when it comes around stars. But relativity also makes a far more extreme prediction of black holes, which are regions of space where gravity is so strong that even light cannot escape. If there are flaws to be found in general relativity, then looking at black holes gives us the best chance to find the cracks. But black holes are black, right? So how can we study them if we can't see them? Well, it turns out it is pretty difficult to see a black hole that's on its own. But if a black hole has an orbiting star, then it can be an entirely different picture. If that star is close enough, then the gravity of the black hole can suck matter off of the star and into a disk of gas around itself, which friction can then heat to millions of degrees C. So these disks represent some of the most extreme objects we can observe in the universe today. So these are what I studied. But in particular, I studied the most extreme of these extreme objects. As a black hole absorbs more and more matter, this disk heats up. So the matter within it emits radiation, more and more radiation. Now, in general, whenever radiation strikes the surface, it exerts a force, but it's a pretty small effect. If you've ever shone a torch under your hand, you can't feel your hand being pushed away. But in these black holes, there is so much radiation that this force can actually balance the gravity of the black hole and stop any more matter falling in. When you think about how much light there has to be to do that, you can imagine that these systems can actually be incredibly bright. So perhaps not surprisingly, considering the extreme nature of the forces involved, these things can show some pretty big variability over time. Sometimes they will fluctuate seemingly at random, sometimes they can dim and brighten in a regular and predictable way, and sometimes they can do one thing for days and then completely change what they're doing. What I want to do is come up with a system of categorizing these objects so we can better try and understand what the physics driving these things are. But why should we care about any of this, right? Because some black hole tens of light years away. Well, I bring you back to general relativity, which was a theory found by looking for flaws in the previous theory of Newtonian mechanics. Perhaps in 1915 it wasn't terribly obvious why anyone should care about relativity, but 100 years in the future, and today we have GPS. Without the physics of general relativity, your GPS position on the ground will pick up an error of 10 kilometers every single day. So next time we fly across the world, land on a mile-long runway, well, maybe you should thank Einstein for helping get you there. What we want to do is go one step further to find whatever lies above general relativity. Well, and who knows what could lie out there, right? So, although it may be a little abstract as to why we should try and be looking for flaws in general relativity right now, perhaps 50 years in the future, people may be barely able to imagine living without technology this kind of research could bring. Thank you.